Bismillah ar-Rahman ar-Rahim. In this video, I am going to explain the linear energy transfer and the difference between the path length and the range, which is going to affect the linear energy transfer. So, simply linear energy transfer is the rate of loss of energy with distance. Because in the previous videos, you have learned the loss of the alpha, positron, negatron, electron capture, and the gamma rays. So now we are going to conclude their laws, and the important point over here is this is the linear energy transfer, which is going to compare the loss of energy by the different ionizing radiations. So this is actually the simple, it is the rate of loss of energy with the distance. So the in case of the electron or the positron, or you can say the beta or the positron or the neutron or the positron, and the other particles are the alpha particles. And if the electrons is going to travel through the material or through the matter, so it is going to be deflected with the negative charges, negative electrons present in the outer shell. So this is called the distance, the path length of the particles. That means path length is the actual distance the particle travels from this point and going to the this point. So this is the path length. But what is the range? Range is the actually what is the actual depth of the penetration in the matter. So if this is the path length, if I consider, okay, this is the depth, and from this point directly to this point, this is the actual depth of penetration in the matter, and this is called the range. So if you have a look at this image, in case of the electron, positron or the negatron, the path length is more as compared to the range. So this is the path length. As you know, this is much more as compared to this is the penetration or the range of the electron in the material. But in case of the uh, alpha particles, alpha particles are heavier and they are not deflected with the electron present in the outer shell. So in this case, the path is equal to the range. So these two important factors should be considered when you are going to discuss the loss of energy by the ionizing radiation. So actually, the important point is the what would be the penetration power of the alpha radiation, and you can have a look over here. The alpha particle is having the same path as compared as the range is having. That means both are equal to each other, but this is not in case of the electron or the negatron. So how can you compare the energy loss by the different radiations, or you can say this is the linear energy transfer in case of the gamma ray, beta particle, or the alpha particle. So amount of energy deposited per unit path length is called the linear energy transfer. So what is the amount transfer or the energy loss per unit path length? So per unit path length is important. So because now you are going to specify with the length, if you give us 1 centimeter to each of the gamma ray, negatron, and the alpha particle, then you can compare which is going to lose more energy as compared to the other. That's why this is called the linear energy transfer, or you can say this is the mean LAT value, because here you can express with the energy per centimeter or energy per angstrom This is the actually the path, the penetration path. It may be in centimeter, angstrom, millimeter, or whatever it is. It depends what the the length you are going to take to compare the penetration power of the radiation. So this is going to depend on the two factor. That means here actually objective is how can you compare the penetration power of the different radiation or their side effect. Which one is more dangerous to us? As I have explained in the first videos, where I have compared the penetration power of the different radiation, and you may watch again that video. But here I'm going to explain this LET of the charged particle is proportional to the square of the charge. That means more will be the charge, more will be the linear energy transfer, because it is going to lose more energy when it is passing through the material, having the interaction with the electrons, and that means it will lose more energy within the material by traveling through the material if the charge on the particle is more. That's why if you compare over here, alpha 0.51 mega electron alpha is having the LET value is for the water, and this is the 13.6 electron volt per angstrom. So this is more. That means alpha is going to ionize more as compared to the beta and the gamma radiation. Why? Because the alpha is having the plus 2 charge, or it is the helium nucleus. So that's why its loss is more as compared to the other. So it is going to create more ions as compared to the other radiation. But this LET is inversely proportional to the kinetic energy, and kinetic energy is the half mv square. That means it is inversely proportional to the velocity. So velocity is actually the penetration power. So it is, if it is the more penetration power, more velocity, then LET will be, the value of LT will be small. And this is the case as mentioned over here. The gamma ray are the photons having more penetration power as compared to the beta, and beta is having more penetration power as compared to the alpha. That's why being a more velocity, its LT value is small as compared to the beta, and beta is small as compared to the alpha. The second important point is here is high LET radiation, alpha particles or the photon, etc., are more damaging to the issue than the low LET radiation in case of the electron, gamma ray, and the X-ray. And this is I have already discussed in the shielding of the different radiations. I will explain over there, but important over here is to explain that point. If it is the more ionizing radiation, that means in case of the alpha particles, they are going to lose more energy. That means their LET is more the ionization power of the alpha radiation. When it is inside the material, it is more, then it is going to damage the tissue more as compared to the beta, and beta is more as compared to the gamma radiation. So you must be very careful if you are working with the radiation. So this is all about the linear energy transfer, or the rate of loss of energy with distance in case of the alpha, beta, and the gamma radiation. So see you in the next video.